Before drifting deeper into tonight's journey, take a moment to look at the night sky. Galaxies contain billions of stars, yet the universe remains overwhelmingly empty. Vast regions stretch across unimaginable distances, where almost nothing exists at all. Tonight, this documentary explores one of astronomy's most surprising mysteries. Why are galaxies so empty if they contain billions of stars? The answer reveals a universe far stranger, larger and more fascinating than it first appears. If relaxing science documentaries help with sleep study or quiet curiosity, please like this video, subscribe to Cosmic Bedtime Stories, and join us for more journeys through the cosmos. Now, as the stars slowly emerge across the darkness, the story begins. The observable universe appears as an immense and continuous expanse, where matter is distributed on scales so large that ordinary intuition about space and fullness no longer applies. On the largest scales currently observed, the universe contains a vast network of structure formed over billions of years as gravity slowly draws matter together. Galaxies are not spread evenly through space, but instead trace a complex pattern shaped by the early conditions of the universe and by the ongoing influence of gravity. Between these concentrations of matter lies an overwhelming amount of space that contains very little visible substance. This contrast between clustered regions and near-empty regions defines the first impression of cosmic emptiness. At this scale, matter is arranged into regions of higher density where galaxies are found, and regions of extremely low density where very few galaxies exist. Observations from large astronomical surveys show that galaxies tend to form along interconnected regions that span hundreds of millions of light years. These regions are not solid structures, but instead loose concentrations of galaxies bound together by gravity and dark matter. The spaces between them are so large that even light travelling at the fastest speed in the universe requires immense periods of time to cross them. These distances contribute directly to the perception of emptiness, because most of the volume of the universe is not occupied by bright, easily detectable matter. The large-scale structure of the universe is often described as a cosmic web. This description reflects how matter is organized into thread-like formations that connect dense regions. Within this web, galaxies act as nodes of concentration, while the connecting regions contain sparse distributions of gas and dark matter. The arrangement is not static, but continues to evolve slowly over cosmic time, as gravity pulls matter inward along these structures. Despite this ongoing movement, the overall impression remains consistent. Most of space contains very little matter compared to the dense regions where galaxies reside. In between these structured regions lie enormous voids. These voids are not completely empty in the absolute sense, but they contain far fewer galaxies and far lower densities of matter than the surrounding filaments. In many cases, a single void can extend across tens or even hundreds of millions of light years. Within such regions, the probability of encountering a galaxy becomes extremely small. The gas that does exist in these voids is typically very diffuse, composed mainly of hydrogen spread thinly across vast distances. This gas does not form stars easily, because it lacks the necessary density for gravitational collapse. The presence of these voids is a key reason why the universe appears empty when viewed at large scales. Although galaxies themselves contain billions of stars, their distribution is highly uneven. When observing a region of space that spans multiple voids, the majority of that region contains no bright structures at all. Only occasional galaxies appear, separated by enormous gaps. This uneven distribution is not accidental, but is a direct consequence of how matter evolved after the early universe transitioned from a nearly uniform state into a structured one driven by gravitational instability. The earlier stages of cosmic structure formation involve tiny fluctuations in density. Over time, these small differences in density grew under the influence of gravity. Regions that were slightly denser attracted more matter, becoming progressively denser, while less dense regions lost matter to their surroundings. This process gradually amplified initial irregularities into the large-scale patterns seen today. As a result, matter became concentrated into specific regions, while other regions became increasingly empty. The universe did not form as a uniform filling of space, but instead developed a highly structured distribution where most volume remains underpopulated. The observable universe as measured by modern instruments and surveys reveals that only a small fraction of its total volume contains galaxies or galaxy clusters. Even within these clusters, matter is not uniformly distributed. Instead, galaxies themselves are separated by large internal distances, and the space between clusters is even greater. This hierarchy of separation contributes to a layered form of emptiness that persists at every scale. From the smallest galactic environments to the largest cosmic structures, empty space dominates volume. Dark matter plays a central role in shaping this structure. Although it cannot be observed directly through emitted light, its gravitational influence guides the formation of cosmic patterns. It forms an invisible framework that helps determine where galaxies can form and how they cluster. This framework enhances the contrast between dense and empty regions by concentrating matter along specific paths while leaving other regions relatively void. Even with this unseen structure, the overall distribution remains sparse when viewed across the full extent of the universe. The expansion of the universe further contributes to this emptiness. As space itself expands, the distances between large-scale structures increase over time. This expansion does not fill space with new matter, but instead stretches the existing distribution, making already sparse regions even more diffuse. Over billions of years, this process enhances the separation between galaxy clusters and deepens the emptiness of cosmic voids. Within this vast structure, galaxies represent only small localized concentrations of matter. Each galaxy occupies a tiny fraction of the total volume of space, while the regions between them dominate the cosmic landscape. The impression of emptiness is therefore not due to a lack of matter in the universe as a whole, but due to the extreme unevenness in how that matter is arranged. Most of the universe is not filled with stars or galaxies, but with vast regions where matter is thinly spread or entirely absent at observable scales. This outermost view of the universe establishes the foundation for understanding cosmic emptiness. It reveals a structure where matter is concentrated into filaments and clusters, separated by immense voids that define the majority of space. The universe at this scale is not uniformly full, but instead shaped by a balance between gravitational attraction, initial density variations, and cosmic expansion, all of which combine to produce a landscape dominated by empty regions. The distribution of galaxies within the observable universe is not random in the sense of being without structure, yet it is also not uniform in the sense of filling space evenly. Instead, galaxies occupy specific regions that reflect the long-term influence of gravity acting on matter since the early stages of cosmic evolution. When viewed across extremely large distances, galaxies appear as scattered points, but closer examination reveals that these points are part of larger patterns that extend far beyond any single galaxy or cluster. The arrangement of these structures contributes directly to the sense that most of the universe is empty. Galaxies tend to cluster together because regions of slightly higher density in the early universe attracted more matter over time. These regions grew into gravitational centers, where gas cooled and condensed, forming stars and eventually entire galaxies. Once formed, galaxies continue to interact gravitationally, drawing one another into groups, clusters, and larger assemblies. These structures are bound by gravity, but the space between them remains largely unfilled by luminous matter. The result is a universe where matter is concentrated into islands separated by vast expanses of low-density space. Within galaxy clusters, multiple galaxies exist in relatively close proximity compared to the wider universe. However, even within these clusters, the distances between individual galaxies are extremely large on human scales. A single cluster may contain hundreds or thousands of galaxies, yet the space within the cluster is still dominated by emptiness. The gravitational influence of the cluster holds these galaxies together, but it does not remove the large gaps between them. Most of the cluster's volume is still not occupied by stars, planets, or dense gas. Beyond clusters lie galaxy groups, which are smaller assemblies containing fewer galaxies. These groups are loosely bound systems where gravitational attraction is weaker, and interactions between galaxies occur over long timescales. Even here, the majority of space remains unfilled. The galaxies move through large regions of low-density space, sometimes interacting or merging, but often separated by distances that far exceed the size of the galaxies themselves. These separations reinforce the perception that matter is sparse across cosmic scales. Between clusters and groups are regions where very few galaxies exist at all. These transitional areas are part of the large-scale structure, but contain far less visible matter. The distribution of galaxies in these regions reflects the underlying gravitational landscape shaped by dark matter. Matter flows along invisible channels toward denser regions, leaving behind areas that become increasingly empty over time. These regions are not completely devoid of matter, but the density is so low that galaxies are rarely found within them. Observational surveys mapping millions of galaxies show that their positions trace a network-like structure rather than a uniform field. This network is composed of dense nodes connected by elongated structures with large gaps in between. The nodes correspond to clusters and superclusters, while the connecting structures are filaments that guide the flow of matter. The gaps between these structures are the voids which occupy most of the universe's volume. This means that although galaxies are numerous in absolute terms, they are confined to a relatively small fraction of space. The clustering of galaxies is influenced by both visible matter and dark matter. Dark matter forms gravitational wells that shape where galaxies can form and persist. These wells act like invisible anchors that pull ordinary matter into specific regions. As a result, galaxies are not spread evenly, but are drawn into patterns defined by the distribution of dark matter. This interaction enhances the separation between dense and empty regions, making the large-scale structure more pronounced over time. Despite the presence of billions of galaxies, the average distance between them is extremely large. If a galaxy were reduced to a small object and placed in a scaled model of the universe, most of the surrounding space would still appear empty, even within a region containing many galaxies. This reflects the fact that galaxies themselves are relatively small compared to the distances that separate them. The luminous parts of galaxies occupy only a tiny fraction of the total volume in which they exist. Within individual galaxies, stars are also widely separated, but at the scale of galaxy distribution, this separation becomes even more extreme. The space between galaxies often contains sparse gas dark matter and occasional intergalactic stars, but these components are extremely diffuse. They do not significantly reduce the overall emptiness of intergalactic space. Instead, they form a faint background presence that fills the gaps without changing their fundamentally low density. The pattern of galaxy distribution continues to evolve over time as gravitational forces pull structures together and cosmic expansion stretches them apart. In some regions, galaxies slowly move toward one another, increasing local density. In other regions, expansion dominates, increasing separation and enhancing emptiness. This dynamic balance shapes the ongoing structure of the universe, but it consistently preserves the overall pattern of clustered matter surrounded by vast empty regions. The distribution of galaxies therefore reveals a universe that is structured but dominated by space rather than matter. The visible components of the universe, including galaxies and their stars, occupy only a small portion of the total volume. The remainder is filled with regions of extremely low density that stretch across immense distances. This imbalance between matter and space is fundamental to understanding why the universe appears empty, even though it contains an enormous number of galaxies. The cosmic web is the large-scale pattern that describes how matter is arranged across the universe when viewed on the greatest observable scales. It is formed not as a solid structure, but as a distribution of matter shaped by gravity, acting over billions of years. In this framework, galaxies and clusters of galaxies are not isolated objects scattered randomly through space, but instead parts of a connected system that outlines where matter has gathered most strongly. The spaces between these connections dominate the total volume of the universe, creating a structure where emptiness is the most common state of space. The cosmic web consists of long, thread-like regions where matter is more concentrated. These regions are called filaments, and they stretch across vast distances, linking clusters of galaxies together. Within these filaments, gas, dark matter and galaxies move slowly under the influence of gravity. Although filaments contain more matter than surrounding regions, they are still extremely thin on cosmic scales. Their density is far lower than anything found inside galaxies, meaning they are not solid structures but diffuse pathways of matter. At the intersections of these filaments lie galaxy clusters. These are regions where multiple filaments meet, allowing matter to accumulate over time. Clusters contain large numbers of galaxies bound together by gravity, along with hot gas that emits X-ray radiation. Even so, the volume within clusters is mostly empty space. The galaxies within them are separated by large distances, and the gas, although hotter and denser than intergalactic medium, still occupies only a small fraction of the cluster's total space. This reinforces the idea that even the densest regions of the cosmic web are not filled in a continuous way. Between the filaments are vast regions known as cosmic voids. These voids occupy most of the volume of the universe and contain far fewer galaxies than average regions. In many voids, galaxies are extremely rare, and the matter density is close to the lowest levels observed anywhere in the universe. These regions are not completely empty, as they still contain thin hydrogen gas and traces of dark matter, but they lack the structures that define filaments and clusters. The dominance of voids is one of the main reasons the universe appears so empty at large scales. The formation of the cosmic web began with small fluctuations in the density of matter shortly after the universe began expanding. These fluctuations were extremely subtle, representing tiny differences in the distribution of matter. Over time, gravity amplified these differences. Slightly denser regions attracted more matter, becoming increasingly dense, while less dense regions became emptier. This process gradually shaped matter into interconnected structures, separated by large empty regions. The result is the network-like pattern observed today. Dark matter plays a central role in defining the cosmic web. It does not emit or absorb light, but it interacts through gravity, forming an invisible framework that guides the movement of ordinary matter. This framework determines where filaments form and how clusters grow. Ordinary matter, including gas and stars, follows the gravitational structure set by dark matter. As a result, the visible universe traces the shape of an underlying invisible network. This network enhances the contrast between dense regions and empty space, by concentrating matter along specific pathways. Within filaments, matter flows slowly toward regions of higher density. Gas moves along these structures, gradually feeding galaxy clusters. However, this flow is not sufficient to fill the surrounding voids. Instead, it reinforces the separation between structured regions and empty space. As matter accumulates in clusters, the surrounding voids become increasingly depleted, further increasing the contrast between dense and empty regions. The cosmic web is dynamic and continues to evolve. Filaments can shift and merge over time while clusters grow through the accumulation of matter and galaxy mergers. At the same time, cosmic expansion stretches the distances between these structures. This expansion does not disrupt the web, but instead increases the scale of its emptiness. Voids expand, filaments thin, and clusters become more isolated relative to one another. The overall structure becomes more pronounced as time progresses. The scale of emptiness in the cosmic web is difficult to comprehend without considering the relative sizes of its components. Filaments span millions of light-years, clusters occupy smaller but still enormous regions, and voids stretch across even larger distances. Despite the presence of these structures, most of the universe's volume is contained within voids. This means that the majority of space in the cosmic web is not occupied by galaxies or dense matter, but by extremely low-density regions. Even within filaments, the matter is not continuous. Gas exists in a highly diffuse state, and galaxies are separated by large internal gaps. This further emphasizes that structure in the universe is hierarchical, with increasing emptiness appearing at larger scales. The cosmic web is therefore not a solid network, but a sparse arrangement of matter within an overwhelmingly empty background. The existence of the cosmic web explains why the universe contains billions of galaxies, yet still appears largely empty. Galaxies are concentrated within a small fraction of space defined by filaments and clusters, while most of the universe exists in voids where matter is extremely rare. This distribution arises naturally from gravitational evolution and continues to persist as the universe expands. The cosmic web represents a balance between structure and emptiness, with emptiness dominating the overall volume. Intergalactic space refers to the regions of the universe that lie between galaxies and their associated clusters extending across distances so large that even entire galaxy groups occupy only a small fraction of this environment. In these regions, matter is present but spread so thinly that it approaches conditions close to a near vacuum on cosmic scales. The study of intergalactic space reveals why the universe appears so empty, even though it contains an enormous number of galaxies distributed across vast distances. The average distance between galaxies is so large that light emitted from one galaxy can travel for millions of years before encountering another significant concentration of matter. This separation means that most photons move through space without interacting with dense material. The space between galaxies is not truly empty, but it contains extremely low-density gas, mostly hydrogen, along with traces of helium and heavier elements dispersed from ancient stellar processes. This gas exists in such small quantities that it does not form visible structures under normal conditions. Within intergalactic space, matter is distributed unevenly. Some regions contain faint gas clouds that are remnants of galaxy formation processes or material ejected from galaxies through energetic events such as supernovae or galactic winds. These clouds are highly diffuse with densities far lower than those found inside galaxies. Even in these regions, atoms are separated by enormous distances, meaning that collisions between particles are extremely rare. This contributes to the overall emptiness of the intergalactic environment. The temperature of intergalactic gas varies depending on its location and history. In some regions, gas is extremely hot due to shock heating caused by gravitational collapse or large-scale structure formation. In other regions, it remains relatively cooler, but still far too diffuse to form stars. Despite temperature differences, the low density remains the defining feature. The energy content of the gas does not compensate for its lack of concentration, so it remains invisible to most optical observations and is primarily studied through indirect methods such as absorption lines in the spectra of distant quasars. Dark matter also permeates intergalactic space, although it does not interact with light. It forms a diffuse background that extends beyond visible structures shaping the gravitational landscape, even in regions that appear empty. This invisible component contributes significantly to the total mass of the universe, but because it does not clump into stars or emit radiation, it does not reduce the apparent emptiness of space. Its presence is inferred only through gravitational effects on visible matter and light. The structure of intergalactic space is influenced by the large-scale cosmic web where filaments of matter connect clusters and galaxies. Between these filaments lie vast voids that dominate the volume of the universe. Intergalactic space often includes both filamentary regions and void regions, but even within filaments, the density remains extremely low compared to galactic environments. As a result, intergalactic space represents a transitional environment between structured regions and the deepest cosmic voids. Galaxies moving through intergalactic space do not encounter significant resistance because the medium is so thin. Even energetic processes such as galaxy collisions or interactions occur over long timescales, reflecting the sparse nature of the environment. Gas stripped from galaxies during such interactions disperses quickly into intergalactic space, spreading over vast volumes and further contributing to its low density. This process slowly enriches intergalactic space with heavier elements, but not enough to change its overall emptiness. Observations of distant light sources passing through intergalactic space reveal the presence of diffuse gas through subtle absorption features. These features indicate that matter is present along the line of sight, but only in extremely small quantities. The majority of space between galaxies does not significantly alter the path of light, reinforcing the idea that intergalactic regions are largely transparent and sparsely populated. This transparency allows astronomers to observe distant galaxies and the early universe with minimal obstruction. The expansion of the universe also plays a role in maintaining the emptiness of intergalactic space. As space expands, distances between galaxies increase, causing matter to become more spread out over time. This expansion does not create new matter, but stretches the existing distribution, making intergalactic regions even less dense. Over billions of years, this process enhances the separation between structures and reinforces the dominance of empty space. Despite its emptiness, intergalactic space is not static. It contains ongoing processes such as the slow movement of gas, the influence of gravitational fields, and the gradual exchange of material between galaxies and their surroundings. However, these processes occur on scales and densities so low that they do not significantly alter the overall character of the environment. The result is a vast region of space where matter exists in a highly diffuse state, continuously shaped, but never concentrated enough to form large structures. Intergalactic space therefore represents one of the clearest examples of cosmic emptiness. It occupies the regions between galaxies extending across immense distances with only trace amounts of matter scattered throughout. The combination of low-density, vast scale, and ongoing expansion ensures that most of the universe's volume remains largely empty, even though galaxies themselves contain vast amounts of matter within their boundaries. Dark matter is introduced as an invisible component of the universe that does not interact with light, but exerts a strong influence through gravity. In the regions between galaxies and within large-scale structures, it forms a vast and diffuse framework that shapes how ordinary matter is distributed. Although it cannot be seen directly, its presence is inferred from the motion of galaxies and the bending of light around massive structures. This unseen material plays a central role in explaining why galaxies are arranged in clustered patterns separated by large empty regions. On the larger scales, dark matter forms extended halos that surround galaxies and galaxy clusters. These halos are much larger than the visible parts of galaxies and extend far into intergalactic space. Within these halos, dark matter is not evenly distributed, but instead forms smooth gradients of density. The gravitational influence of these halos determines how galaxies rotate, and how they remain bound together within clusters. Without dark matter, the observed motions of galaxies would not match the amount of visible matter alone. Between these halos lies a vast network of lower density dark matter that connects larger structures. This network aligns with the filaments of the cosmic web guiding the flow of gas and galaxies over time. Ordinary matter follows the gravitational pull of dark matter, gradually accumulating in regions where dark matter density is higher. This process reinforces the separation between dense regions and surrounding emptiness, as matter is continuously drawn into specific gravitational wells, while leaving other regions increasingly sparse. Dark matter does not emit, absorb, or reflect electromagnetic radiation, meaning it does not contribute to the brightness of any region of space. As a result, even regions rich in dark matter can appear completely empty when observed through telescopes. This invisibility makes it a fundamental reason why large portions of the universe seem devoid of matter, even though significant mass exists in those same regions in an unseen form. Within galaxy clusters, dark matter forms the dominant source of gravitational binding. The visible galaxies and hot gas represent only a small fraction of the total mass. The rest is contained in an extended dark matter halo that spans far beyond the visible boundaries of the cluster. This halo shapes the structure of the cluster and maintains its stability over long timescales. However, the volume occupied by this halo is still mostly empty of ordinary matter, reinforcing the sense that even massive structures are largely composed of space rather than substance. On intergalactic scales, dark matter forms a scaffold that connects clusters and filaments. This scaffold is not a solid structure, but a statistical distribution of mass that influences how matter moves through space. Regions of slightly higher dark matter density act as attractors pulling in gas and galaxies over billions of years. These attractors define the paths along which cosmic structures grow, while surrounding regions remain underdense and empty. The relationship between dark matter and ordinary matter is one of gravitational coupling. Ordinary matter responds to the gravitational field created by dark matter, gradually settling into regions where the potential energy is lower. Over time, this leads to the formation of galaxies within dark matter halos and clusters at the intersections of large dark matter filaments. This process naturally leaves large regions of space with little ordinary matter, contributing to the overall emptiness of the universe. In cosmic voids, dark matter density is significantly lower than in filaments and clusters, but it is not entirely absent. Even these regions contain a faint background distribution of dark matter that reflects the initial conditions of the early universe. However, because this distribution is so diffuse, it does not lead to the formation of galaxies or other visible structures. As a result, voids remain dominated by empty space, with only minimal matter present. The influence of dark matter extends to the evolution of cosmic expansion. While dark matter itself does not drive expansion, its gravitational effects shape how structures respond to it. In regions where dark matter is concentrated, gravity can slow or reverse local expansion, leading to the formation of bound systems. In underdense regions, expansion proceeds more freely, increasing separation between structures and enhancing emptiness over time. Simulations of cosmic evolution show that without dark matter, the universe would not form the same large-scale structure. Galaxies would be more evenly distributed, and the contrast between dense and empty regions would be significantly reduced. With dark matter present, however, matter becomes highly concentrated along specific pathways, leaving vast regions with very little ordinary matter. This leads to a universe where emptiness is the dominant feature at large scales. Although dark matter contributes most of the universe's mass, it does not reduce the emptiness of space in a visible sense. Instead, it deepens the structure of emptiness by organizing matter into sharper contrasts between dense and sparse regions. The result is a universe where most matter is hidden in invisible form, while most space remains devoid of detectable structures. Dark matter therefore acts as both a structuring force and a contributor to cosmic emptiness. It shapes where galaxies form and how they cluster, while simultaneously leaving vast regions of space without visible matter. This dual role helps explain why the universe contains so many galaxies, yet still appears overwhelmingly empty when viewed on the larger scales. The formation of galaxies begins in the early universe when matter is still relatively smooth, but contains tiny variations in density that grow over time under the influence of gravity. At this stage, the universe is filled with hot gas composed mainly of hydrogen and helium, spread almost uniformly but not perfectly so. These slight differences in density are crucial because they determine where matter will eventually gather and where it will remain sparse. Over billions of years, these small fluctuations develop into the large structures that define the present universe. As gravity acts on slightly denser regions, those regions begin to attract more matter from their surroundings. Gas slowly flows inward, increasing the density further and accelerating the process of collapse. This feedback effect means that once a region becomes slightly denser than average, it tends to grow denser over time. Meanwhile, surrounding regions lose matter, becoming increasingly diffuse. This unequal distribution of matter leads to the emergence of distinct structures separated by large empty spaces. In the early stages of collapse, gas clouds form within regions of higher density. These clouds are vast, spanning hundreds of thousands of light years, and contain enough material to eventually form entire galaxies. As the gas continues to collapse, it cools and condenses, allowing gravity to pull it into smaller and more compact structures. Within these collapsing regions, the first stars begin to form, marking the transition from diffuse gas to structured luminous objects. The formation of stars is a key step in galaxy formation. As gas collapses under gravity, pressure and temperature increase until nuclear fusion begins in the cores of dense regions. These early stars release energy and begin to shape their surroundings through radiation and stellar winds. However, even as stars form, most of the surrounding space remains empty. The newly formed stars are separated by large distances, and the gas between them is still extremely diffuse. As more stars form, they begin to group together into larger structures. These stellar groups gradually evolve into galaxies as gravity continues to pull material inward. The process is not instantaneous, but occurs over extended periods during which matter becomes increasingly concentrated in certain regions while other areas are depleted. This uneven accumulation of matter is what leads to the formation of distinct galaxies rather than a uniform distribution of stars. Within forming galaxies, the distribution of matter is not uniform. Dense regions collapse more quickly, forming the central bulges and early galactic cores. Surrounding regions take longer to settle and form extended structures such as disks and halos. Despite this internal structure, most of the space within a forming galaxy remains empty. The distances between individual stars are enormous compared to their sizes, and even in dense regions, space dominates volume. The role of dark matter is essential in guiding galaxy formation. Dark matter halos form, first creating gravitational wells into which ordinary matter falls. These halos act as scaffolding for galaxy formation, determining where gas will accumulate and collapse. Without this invisible framework, the distribution of galaxies would be far more uniform, and the large-scale emptiness of the universe would be significantly reduced. Instead, dark matter concentrates matter into specific regions, reinforcing the separation between galaxies. As galaxies form, feedback processes begin to influence their evolution. Energy released by young stars, supernovae, and black holes can push gas outward, preventing all available matter from collapsing into stars. This feedback helps regulate star formation and contributes to the persistence of empty space within and around galaxies. Even as galaxies grow in mass, they remain surrounded by large regions where matter is too diffuse to form new stars. The growth of galaxies also depends on mergers and interactions. Smaller galaxies are gradually pulled into larger ones through gravitational attraction. These events can trigger bursts of star formation, but they also redistribute matter across large volumes of space. Even after mergers, galaxies do not become fully dense objects. Instead, they remain separated systems embedded in vast empty environments. The process of galaxy formation naturally leads to a universe where matter is concentrated in discrete structures rather than spread evenly. This is because gravity amplifies initial differences rather than smoothing them out. Over time, dense regions become denser, while empty regions become emptier. This divergence creates the large-scale pattern of galaxies separated by vast voids that defines the observable universe. Even at the end of galaxy formation, most of the universe's volume remains unfilled by stars or dense gas. Galaxies occupy only a small fraction of space, and the regions between them remain largely empty. This outcome is not accidental, but is a direct result of gravitational evolution acting on the early universe's initial conditions. The formation of galaxies therefore explains not only the presence of structure, but also the dominance of emptiness at cosmic scales. Inside galaxies, matter is arranged in a way that appears rich in structure when viewed from within, yet it remains overwhelmingly empty when considered by volume. A galaxy is a gravitationally bound system, composed of stars, gas dust, dark matter, and remnants of past stellar evolution. Although it contains billions of stars, these stars are not closely packed together. Instead, they are separated by distances so large that most of the internal volume of a galaxy is empty space. The structure of a typical galaxy includes a central region known as the bulge, a surrounding disk in many cases, and an extended halo. The bulge contains a higher concentration of stars, but even here, stars are separated by vast distances relative to their size. The disk region, which often contains spiral arms, is where new stars form from dense clouds of gas and dust. Despite the appearance of brightness and structure, the disk is still mostly empty space, with matter concentrated in thin regions compared to the total volume it occupies. The halo of a galaxy extends far beyond the visible disk. It contains old stars, globular clusters, and a large amount of dark matter. The stellar density in the halo is extremely low, and the distances between stars can be so large that they are effectively isolated in space. This extended region highlights how much of a galaxy's volume is not occupied by luminous matter. The halo's presence increases the overall size of the galaxy significantly, without adding much visible structure. Within the disk, stars are organized into patterns such as spiral arms, But these structures are not solid formations. Spiral arms are regions of higher density, where gas and stars are more concentrated, but they are still composed mostly of empty space. Stars move through these arms over time rather than remaining fixed within them. The appearance of structure arises from density waves that compress material locally, but between these regions space remains sparse. The interstellar medium fills the space between stars within a galaxy. This medium consists of gas and dust, primarily hydrogen, with traces of heavier elements. Although it plays an essential role in star formation, its density is extremely low. At most locations, atoms are separated by distances far greater than those found in everyday environments. This means that even within galaxies, the material content is spread very thinly compared to the size of the system. Star formation occurs only in the densest parts of the interstellar medium, where gravity can overcome internal pressure and cause collapse. These regions are relatively rare compared to the overall volume of a galaxy. Molecular clouds where star formation takes place occupy only small fractions of galactic space. The rest of the interstellar medium remains too diffuse to form new stars, reinforcing the dominance of empty space. The motion of stars within a galaxy is governed by gravity, causing them to orbit the galactic center. These orbits take place in a largely empty environment, where direct interactions between stars are extremely rare. Even though billions of stars are present, the distances between them are so large that collisions are highly unlikely. Most stars move through space without ever encountering another star directly during their lifetimes. Dark matter continues to play an important role within galaxies by forming extended halos that dominate their mass. These halos are far larger than the visible parts of galaxies and extend into regions where there are few or no stars. The gravitational influence of dark matter determines the overall structure and rotation of galaxies, but it does not reduce the emptiness of space within them, since it does not form compact structures like stars or planets. Galactic evolution involves slow changes over time, including the formation of new stars, the death of old stars, and the gradual redistribution of gas. However, these processes occur within a framework where most space remains empty. Even energetic events such as supernovae or black hole activity affect only localized regions, leaving the majority of galactic volume unchanged in its low-density state. The overall impression of a galaxy as a dense collection of stars is therefore misleading when considering scale. From a distance, galaxies appear bright and structured, but internally they are dominated by empty space. The stars, gas clouds, and dust occupy only a small fraction of the total volume. This internal emptiness mirrors the larger emptiness between galaxies, reinforcing a consistent pattern across all cosmic scales. The structure of galaxies demonstrates that matter in the universe is organized into discrete, separated systems rather than continuous distributions. Even within these systems, emptiness remains the dominant feature. This internal sparsity contributes to the broader understanding of why the universe appears empty. Despite containing vast numbers of stars and galaxies, stars within galaxies represent the most familiar visible components of cosmic structure, yet their distribution reveals a profound level of emptiness when examined in detail. Each star is a massive sphere of plasma held together by gravity and powered by nuclear fusion in its core. Although stars appear numerous when viewed collectively, they are separated by distances so vast that the space between them dominates the internal volume of a galaxy. In most galaxies, stars are not clustered tightly together, but are instead spaced at intervals measured in light years. A light year is the distance light travels in 1 year, and even the nearest neighboring stars are separated by several light years. This means that between any two stars there is an immense region of nearly empty space, containing only sparse gas and dust. The scale of separation ensures that direct interactions between stars are extremely rare. The distribution of stars varies depending on their location within a galaxy. In central bulges, stars are more densely packed than in outer regions, yet even in these dense areas, the space between stars remains vast compared to their physical size. In galactic disks, stars are distributed across large, thin regions where density waves influence their arrangement, but the overall structure is still dominated by empty space. In outer halos, stars are even more widely separated, often existing as isolated objects in near-vacuum conditions. Star systems often form with multiple stars bound together by gravity, but these systems are small compared to the distances between systems. Binary and multiple star systems exist within localized regions, yet they occupy only a tiny fraction of a galaxy's volume. Beyond these systems, the distances between independent stars remain so large that space is effectively continuous emptiness on human scales. The formation of stars begins in dense regions of molecular clouds, where gas and dust accumulate under gravity. These clouds are among the densest regions in a galaxy, yet they are still extremely diffuse compared to any terrestrial environment. Within these clouds, small regions collapse to form protostars, which eventually ignite nuclear fusion. Once formed stars drift away from their birth clouds, leaving behind large regions of space that return to low-density conditions. As stars evolve, they move through the galaxy, following orbital paths shaped by the gravitational potential of the galactic disk and dark matter halo. These orbits take place in an environment where encounters with other stars are rare. Even over billions of years, most stars will not pass close enough to another star to significantly alter their trajectory. This emphasizes how empty the internal environment of a galaxy truly is. The space between stars is filled with the interstellar medium, but this medium is extremely thin. It consists primarily of hydrogen atoms along with small amounts of helium and heavier elements. The density is so low that atoms are widely separated, making collisions infrequent. In many regions, the interstellar medium is nearly indistinguishable from a vacuum, especially when compared to conditions required for matter to behave as it does on planetary surfaces. Supernova explosions and stellar winds contribute material to this interstellar environment, but even these energetic processes do not significantly increase its density on a galactic scale. Instead, they disperse matter across large volumes of space, maintaining the overall low-density character of the galaxy. This process ensures that while material is constantly recycled, it never accumulates enough to fill the space between stars. The apparent brightness of the night sky from within a galaxy can create the impression of abundance, but this brightness comes from isolated points of light separated by immense darkness. The darkness corresponds to the vast empty regions between stars which make up most of the galaxy's volume. Even though billions of stars are present, the gaps between them dominate spatial structure. Gravitational interactions between stars are limited by distance. Only in rare cases do stars pass close enough to significantly affect one another. Most stellar motion occurs in smooth orbits, influenced by the overall mass distribution of the galaxy rather than by direct encounters. This further reinforces the idea that space between stars is not a crowded environment, but a largely empty one. The overall structure of stellar distribution shows that galaxies are not filled volumes but sparse systems where matter is concentrated in discrete points, separated by vast empty regions. This pattern is consistent throughout the galaxy from dense central regions to sparse outer halos. The dominance of empty space at the stellar level mirrors the larger emptiness found between galaxies, creating a continuous hierarchy of sparsity across cosmic scales. Planetary systems form within galaxies as secondary structures around individual stars, Yet even these systems are dominated by empty space when examined at their true scale. A planetary system consists of a central star, planets, moons, asteroids, comets, and dust, all bound together by gravity. Despite the presence of multiple bodies, the vast majority of the system's volume is not occupied by solid matter, but by near-vacuum space through which these objects move. The central star contains almost all of the mass of a planetary system, while planets and smaller bodies account for only a small fraction. Even so, the distances between the star and its planets are extremely large compared to the sizes of the planets themselves. In many systems, the distance between the star and the outermost planet spans billions of kilometers. Within these distances, most of space contains very little material, with particles spread thinly across enormous volumes. Planets orbit their star along paths that are largely empty. These orbits are stable over long timescales because gravitational forces act across empty space without requiring a medium. The space between planets is not filled with matter in any continuous sense, and even within planetary orbits, the density of dust and gas is extremely low. This creates a system where motion occurs through vast regions of near vacuum. Within planetary systems, smaller structures such as asteroid belts and cometary reservoirs contain higher concentrations of minor bodies. However, even these regions are mostly empty space. In asteroid belts, for example, individual asteroids are separated by millions of kilometers on average. Collisions are rare, and most asteroids travel through space without encountering others for long periods of time. Cometary regions located at the outer edges of systems contain icy bodies spread across enormous distances, further illustrating the sparsity of matter. The formation of planetary systems begins in protoplanetary disks, which are rotating disks of gas and dust surrounding young stars. These disks are relatively dense compared to interstellar space, but they are still extremely thin compared to terrestrial environments. Over time, particles within these disks collide and stick together, gradually forming larger bodies. This process eventually leads to the formation of planets, but it leaves behind vast regions of empty space, where material has either been incorporated into larger objects or dispersed. Even during the early stages of planetary formation, most of the disk remains empty. Only certain regions within the disk reach densities sufficient for planet formation. These regions collapse into solid bodies while the surrounding space remains sparsely populated. As planets grow, they clear their orbits of smaller debris, further increasing the emptiness of their surrounding regions. Moons and satellites form through similar processes, either from material left over during planet formation or from captured objects. These systems are also dominated by empty space. The distances between moons and their parent planets are large compared to their sizes, and the regions between different planetary orbits are even more vast. Each planetary system therefore contains multiple layers of emptiness, from the scale of individual orbits to the space between planets. The influence of the star's gravity extends far beyond the visible planets, defining a large region known as the gravitational boundary of the system. Within this region, objects can remain bound to the star even at extreme distances. However, most of this space contains very little matter, reinforcing the idea that gravitational influence does not imply physical fullness. Instead, it defines a region of control over largely empty space. Radiation from the central star fills planetary systems with energy but not with matter. Light and charged particles travel through space without significantly increasing its density. Solar winds spread thin streams of particles across the system, but these particles are widely dispersed and do not create dense environments. This maintains the overall emptiness of interplanetary space despite continuous energetic activity. The motion of objects within planetary systems occurs in a stable balance between gravitational attraction and inertia. This motion takes place through space that is almost entirely empty, with very few interactions between objects. Collisions are rare events over astronomical timescales, further emphasizing the lack of material density in these regions. Planetary systems therefore represent a scaled-down version of the same pattern seen across the universe. Matter is concentrated in central stars and smaller orbiting bodies, while the space between them remains overwhelmingly empty. This structure mirrors the larger cosmic pattern of galaxies separated by vast voids, reinforcing the idea that emptiness is a fundamental characteristic of structure at every scale. The interstellar medium is the diffuse material that exists between stars within a galaxy, and it represents one of the most important components for understanding why even galaxies themselves are largely empty in volume. Although it contains gas dust and cosmic rays, its density is so low that it resembles a near vacuum when compared to any environment familiar on planetary scales. This medium fills the space between stellar systems, but it does so in an extremely thin and uneven distribution. Most of the interstellar medium is composed of hydrogen in atomic or molecular form, with helium and trace heavier elements also present. These particles are spread across enormous distances, meaning that collisions between atoms are rare. In many regions, a single cubic centimetre of space may contain only a few atoms or even fewer. This extreme sparsity means that light and radiation can travel through these regions with minimal interaction, allowing distant astronomical objects to be observed clearly. The interstellar medium is not uniform but exists in different phases depending on temperature, density, and radiation exposure. Some regions are cold and dense, forming molecular clouds where stars can eventually form. These clouds, although dense relative to their surroundings, are still extremely thin compared to any Earth-based environment. Other regions are warm and partially ionized, while some are hot and highly diffuse, created by energetic processes such as supernova explosions. Despite these differences, all phases share the defining feature of very low density. Within molecular clouds, gas and dust begin to clump under gravity, leading to the formation of new stars. However, even these star-forming regions occupy only a small fraction of the total volume of the interstellar medium. The majority of space between stars remains in a diffuse state where matter is too spread out to collapse. This imbalance ensures that star formation is limited to specific regions rather than occurring everywhere. Dust grains within the interstellar medium are tiny solid particles composed of carbon, silicon, oxygen, and other elements. These grains play an important role in cooling gas and enabling molecular formation, but they are extremely sparse. Even in dusty regions, the distance between grains is vast on microscopic scales. As a result, dust does not form continuous clouds in the way clouds appear in Earth's atmosphere, but instead exists as a thin scattering of particles across space. The interstellar medium also contains regions of hot ionized gas created by energetic events. Supernova explosions inject large amounts of energy into surrounding space, heating gas to extremely high temperatures. Despite this energy, the density remains low, so the gas expands and becomes even more diffuse. These hot regions can extend across large portions of a galaxy filling space without significantly increasing its matter content. Magnetic fields permeate the interstellar medium and influence the motion of charged particles. These fields help shape the structure of gas and dust, guiding their movement along large-scale patterns. However, magnetic fields do not add matter to space, and therefore they do not reduce its emptiness. Instead, they organize already sparse material into filaments and clouds within an overall low-density environment. Cosmic rays, which are high-energy particles traveling through space, also pass through the interstellar medium. These particles move freely across vast distances, rarely interacting with other matter, due to the extreme sparsity of the environment. Their ability to traverse entire galaxies with minimal obstruction highlights how empty interstellar space truly is. The interstellar medium plays a crucial role in the life cycle of galaxies, recycling material from dying stars into new generations of stars and planets. However, this recycling occurs within a framework where most of the volume remains empty. Material is continuously redistributed, but it never accumulates uniformly across space. Instead, it cycles through dense and diffuse regions, maintaining the overall structure of sparsity. Even within a single galaxy, the interstellar medium dominates the volume between stars. While stars and planetary systems are concentrated into small regions, the space surrounding them is filled mostly with this thin, diffuse material. This means that the visible structure of a galaxy represents only a small fraction of its total physical space. The interstellar medium therefore serves as a bridge between dense stellar regions and the vast emptiness of intergalactic space. It is not a solid or continuous substance, but a sparse distribution of particles that fills space without occupying it in any dense form. Its existence demonstrates that even within galaxies, emptiness remains the dominant characteristic of cosmic structure. Star formation regions exist as localized concentrations within the interstellar medium, where gas and dust become sufficiently dense for gravity to overcome internal pressure. These regions are rare compared to the total volume of a galaxy, yet they are essential for the creation of new stars. They form within molecular clouds, which are cold, dark structures, composed primarily of hydrogen molecules mixed with dust grains and trace elements. Despite their relative density compared to surrounding space, they remain extremely diffuse by ordinary physical standards. Within these molecular clouds, gravity slowly draws material together. Small irregularities in density grow over time, causing certain areas to become slightly more concentrated than others. As these regions gain mass, their gravitational pull strengthens, drawing in additional gas from the surrounding cloud. This gradual accumulation of matter leads to the formation of dense cores, which eventually collapse under their own gravity to form protostars. However, most of the cloud does not participate in this collapse, leaving large regions of empty space within and around star-forming areas. Star formation is an inefficient process in terms of volume. Only a small fraction of a molecular cloud's material ends up forming stars, while the rest remains diffuse or is dispersed by stellar feedback. Radiation, stellar winds, and eventual supernova explosions from newly formed stars push surrounding gas outward, disrupting nearby regions and preventing further collapse. This feedback maintains the overall low density of the interstellar medium and contributes to the persistence of empty space even in active star-forming regions. Dense cores within molecular clouds are the direct sites of star formation. These cores are relatively small compared to the cloud as a whole, and are often separated by large distances. Within each core, gas continues to collapse until temperatures and pressures become high enough for nuclear fusion to begin. Once a star ignites, it begins to influence its surroundings, but the vast majority of space around it remains unchanged in its low-density state. Filaments of gas within molecular clouds often serve as channels where material is funneled into star-forming regions. These filaments are long, thin structures that connect denser cores. Even within these filaments, the density is low compared to any solid or atmospheric environment. They represent slight enhancements in an otherwise extremely sparse medium rather than fully filled structures. The life cycle of molecular clouds is relatively short on cosmic timescales. Over millions of years, star formation and feedback processes gradually disperse the cloud-returning material to the broader interstellar medium. This dispersal spreads matter thinly across space, reinforcing the overall emptiness of the galaxy. Only a small fraction of the original cloud becomes permanently bound in stars or planets. Temperature variations within star formation regions also influence their structure. Cold regions allow gas to remain stable and dense enough to collapse, while warmer regions resist compression and remain diffuse. Even in colder zones, however, the absolute density remains extremely low compared to everyday environments. This ensures that even the most active star-forming regions are still dominated by empty space. Magnetic fields within molecular clouds add another layer of structure by guiding the movement of charged particles. These fields can support parts of the cloud against gravitational collapse, slowing the formation of stars. This additional support contributes to the persistence of large volumes of diffuse gas that do not form stars, further increasing the proportion of empty space within the cloud. Turbulence within molecular clouds creates complex internal motion. Gas flows in chaotic patterns, forming regions of compression and rarefaction. These turbulent motions generate localized density enhancements, where stars may eventually form. However, most of the cloud remains in a low-density state, and turbulence does not significantly increase the overall matter concentration of the region. The formation of stars within these regions is therefore highly localized. While clusters of stars may emerge from a single molecular cloud, they represent only a small fraction of its volume. Once star formation is complete, the remaining gas is dispersed into surrounding space, leaving behind an even more diffuse environment than before. Star formation regions thus illustrate a key principle of cosmic structure: density is the exception, not the rule. Even in the places where matter is most concentrated within galaxies, emptiness still dominates the overall volume. The process of star formation briefly increases local density, but it ultimately contributes to the redistribution of matter across larger, emptier regions of space. This dynamic cycle of collapse and dispersal ensures that galaxies remain largely empty systems despite ongoing star formation. Dense regions appear and disappear over time, but they never fill the galaxy as a whole. Instead, they exist as temporary concentrations within an overwhelmingly sparse environment. Radiation and energy fields within galaxies form an invisible but pervasive environment that fills space without adding significant matter to it. These fields arise from stars' supernovae accretion processes around black holes and the general background of electromagnetic emission produced throughout galactic history. Although this energy can travel across vast distances, it does not reduce the emptiness of space because it carries energy rather than substantial mass in a concentrated form. Stellar radiation is the most widespread source of energy within a galaxy. Every star emits light and other forms of electromagnetic radiation as a result of nuclear fusion in its core. This radiation spreads outward in all directions, passing through the interstellar medium and filling the galaxy with a diffuse field of energy. Despite its omnipresence, it does not increase the density of matter, and it does not create physical structure in the space it occupies. In addition to steady stellar radiation, energetic events such as supernovae inject large amounts of energy into surrounding space. When massive stars reach the end of their life cycles, they release enormous bursts of radiation and eject material at high speeds. This material expands into the interstellar medium, forming shock waves that heat and compress nearby gas. However, these effects are localized and temporary. Over time, the ejected material disperses, and the surrounding space returns to a low-density state. Black holes contribute to the energetic environment of galaxies through accretion processes. When matter falls into a black hole, it forms an accretion disk that becomes extremely hot due to friction and gravitational compression. This disk emits intense radiation across multiple wavelengths. Even so, the region of influence remains small compared to the size of the galaxy, and most of the surrounding space remains unaffected in terms of matter density. The radiation fields within galaxies interact with the interstellar medium, but do not significantly alter its overall structure. Photons travel through space without requiring a medium, and they rarely interact with the sparse gas and dust that exists between stars. As a result, energy can permeate large regions of space while leaving them physically empty. This separation between energy flow and matter distribution is a key reason why space can be both active and empty at the same time. Cosmic rays also contribute to the energetic environment. These high-energy particles travel through galaxies at near relativistic speeds, crossing vast distances with minimal interaction. Although they carry significant energy, their number density is extremely low, meaning they do not contribute meaningfully to the filling of space. Instead, they pass through the interstellar medium, occasionally interacting with atoms, but mostly traveling unimpeded. Magnetic fields within galaxies influence the movement of charged particles, shaping the paths of cosmic rays and guiding the flow of ionized gas. These fields extend over large regions of space, forming complex patterns that reflect the underlying structure of the galaxy. However, magnetic fields themselves do not contain matter, and their presence does not reduce the emptiness of space. They represent force structures rather than material ones. The interaction between radiation, cosmic rays, and interstellar matter creates a dynamic but low-density environment. Energy is constantly moving through space, but matter remains sparse. This means that galaxies are not static voids, but active regions where energy flows continuously through largely empty regions. The presence of energy does not equate to fullness in a physical sense, because the fundamental emptiness of space is defined by the absence of concentrated matter. In some regions, particularly near energetic sources, radiation can heat and ionize gas, creating visible structures such as nebulae. These structures appear dense in images, but they are still extremely diffuse compared to everyday matter. Their brightness comes from energy interactions rather than high material density. Even within these glowing regions, most of the volume remains empty. The large-scale distribution of radiation across a galaxy forms a faint background glow that permeates space. This background is the cumulative result of countless stars and energetic events over cosmic time. Despite its wide presence, it does not accumulate into dense structures. Instead, it diffuses across space, maintaining the low-density character of the galaxy. Energy fields therefore coexist with matter in a way that highlights rather than reduces emptiness. They fill space in terms of influence and radiation, but not in terms of physical substance. The result is a galaxy that is active and energetic, yet overwhelmingly empty when measured by matter content. This distinction between energy presence and material density is essential to understanding why space appears so empty, even within regions of intense astrophysical activity. Gravitational binding within galaxies and larger cosmic structures determines how matter collects, remains stable, and resists the dispersing influence of cosmic expansion. Gravity acts between all forms of matter and energy that possess mass, drawing them together over time. In regions where matter is sufficiently concentrated, gravity overcomes internal motion and leads to the formation of bound systems, such as stars, planetary systems, galaxies, and clusters of galaxies. However, most of space does not contain enough matter for gravity to create compact structures, leaving vast regions effectively empty. Within galaxies, gravity is strong enough to hold billions of stars in orbit around a central mass distribution. This includes both visible matter and the much larger contribution from dark matter. Despite this binding force, the distribution of matter remains highly uneven. Stars are held within the galaxy's gravitational potential, but they are spread across enormous distances. Gravity maintains the structure of the galaxy without filling the space inside it, meaning that binding and emptiness coexist at the same time. On smaller scales, gravitational binding becomes more apparent in systems such as star clusters and binary star systems. In these environments, gravity draws objects closer together, increasing local density. However, these systems are rare compared to the vast regions of space, where gravitational attraction is too weak to overcome separation distances. As a result, most of the universe exists in a state where gravity is present, but not strong enough to create dense structures. The strength of gravity decreases with distance, which means that its ability to bind matter depends heavily on how closely matter is distributed. In regions where matter is sparse, gravitational forces are too weak to significantly alter motion. This leads to large volumes of space where objects move independently through near-vacuum conditions without strong interaction. These regions contribute significantly to the overall emptiness of the universe. Galaxy clusters represent the largest gravitationally bound structures in the universe. Within these clusters, gravity holds together hundreds or thousands of galaxies, along with large amounts of hot gas and dark matter. Even so, most of the cluster's volume is not filled with dense material. The space between galaxies within a cluster remains extremely large, and the hot gas that permeates the cluster is highly diffuse compared to any solid or liquid state of matter. Beyond clusters, gravity becomes weaker relative to cosmic expansion. In these regions, matter is not strongly bound and can be carried apart as space itself expands. This expansion increases the distances between structures over time, making already sparse regions even more empty. Gravity still operates, but it is often insufficient to counteract the stretching of space on large scales. The interplay between gravity and expansion defines the large-scale structure of the universe. In dense regions, gravity dominates and leads to the formation of bound systems. In underdense regions, expansion dominates, causing matter to spread out further. This balance results in a universe where matter is concentrated into discrete structures separated by vast, empty regions. Dark matter significantly enhances gravitational binding in regions where it is present. Its additional mass strengthens the gravitational potential of galaxies and clusters, helping to hold them together. Without it, many structures would not remain stable over long timescales. However, even with dark matter, the distribution of matter remains highly uneven, and large volumes of space remain unoccupied by dense material. Gravitational potential wells created by matter distributions determine where galaxies can form and persist. These wells act as regions where matter naturally accumulates. Outside these wells, matter is more freely distributed and less likely to form structures. This leads to a cosmic landscape in which dense regions are separated by extensive areas of low density. The formation of structure under gravity is inherently hierarchical. Small objects such as stars form first, followed by larger systems such as galaxies and finally galaxy clusters. At each level, matter becomes more concentrated in specific regions, while leaving surrounding space increasingly empty. This hierarchical process reinforces the dominance of empty space at every scale, above the smallest bound systems. Even within gravitationally bound systems, motion does not eliminate emptiness. Stars orbit within galaxies, planets orbit within star systems, and galaxies orbit within clusters. Yet all of these motions occur through vast regions of near vacuum. Gravity defines structure and motion, but it does not fill space with matter. The dominance of gravity in shaping structure therefore leads paradoxically to a universe where most space remains empty. By drawing matter into discrete regions and leaving other regions sparsely populated, gravity enhances contrast rather than uniformity. This results in a cosmos where structure is concentrated and emptiness is widespread, even though gravitational influence extends throughout all space. The expansion of the universe is a fundamental feature of cosmic evolution, in which the fabric of space itself increases in scale over time. This expansion does not involve galaxies moving through a fixed background, but instead describes how distances between large-scale structures grow as space stretches. As a result, regions of the universe that were once closer together become progressively more separated, increasing the overall emptiness of space on the larger scales. On cosmological scales, expansion affects the distribution of galaxies and galaxy clusters by increasing the distances between them. Even though gravitationally bound systems remain intact, the space between these systems grows larger. This leads to a gradual dilution of matter across vast regions. The galaxies themselves do not expand internally in the same way because local gravitational forces hold them together, but the empty space between them continues to increase. The rate of expansion is not uniform in its effects on structure. Within galaxies and clusters, gravity dominates and prevents expansion from pulling structures apart. However, in regions where matter is not gravitationally bound, expansion becomes the dominant influence. In these areas, distances increase over time and matter becomes more spread out. This results in large regions of extremely low density, reinforcing the perception of emptiness across cosmic scales. As expansion continues, light traveling through space experiences increasing redshift, meaning its wavelength becomes longer as it moves through expanding space. This effect reflects the stretching of space itself, rather than motion through a static medium. While this phenomenon affects the energy of light, it does not add matter to space or reduce its emptiness. Instead, it highlights the dynamic nature of an environment that remains largely empty in terms of physical substance. The influence of expansion becomes more significant at greater distances. Nearby galaxies within gravitationally bound groups are relatively unaffected, but distant galaxies recede from each other at increasing rates. Over extremely large scales, this leads to regions where galaxies move beyond observable range over time. These regions become increasingly isolated, with vast empty spaces forming between observable structures. Cosmic voids expand along with the universe, becoming larger and more empty over time. These voids, already characterized by extremely low matter density, grow as surrounding filaments and clusters are pulled apart by expansion. The result is a universe where the largest structures become more separated, and the empty regions between them become more dominant. The balance between gravity and expansion determines the large-scale fate of cosmic structure. Gravity binds matter into galaxies and clusters, while expansion stretches unbound regions. In areas where gravity is strong, structure remains intact, but in regions where gravity is weak, expansion leads to increasing emptiness. This dual effect ensures that matter remains concentrated in specific regions, while empty space expands around it. Dark energy, a component associated with the accelerated expansion of the universe, influences this process by increasing the rate at which space expands over time. While its exact nature remains uncertain, observations indicate that expansion is not slowing, but accelerating on large scales. This acceleration enhances the separation between distant structures, contributing further to the dominance of empty space in the universe. As expansion progresses, the overall density of matter decreases when averaged across large volumes of space. This does not mean that matter disappears, but rather that it becomes more widely distributed. The same amount of matter occupies an ever-increasing volume, leading to lower average density and greater separation between structures. This process reinforces the appearance of emptiness even in a universe filled with galaxies. The long-term effects of expansion lead to increasing isolation of galaxies. Over time, distant galaxies move beyond the reach of observable regions, leaving local structures as isolated islands in an ever-expanding void. Within these regions, gravitationally bound systems remain intact, but the surrounding space becomes increasingly empty and unreachable. Expansion therefore acts as a large-scale mechanism that enhances the pre-existing structure of emptiness created by gravitational clustering. While gravity concentrates matter into galaxies and clusters, expansion spreads these structures apart, ensuring that most of the universe's volume remains unfilled by dense matter. The combination of these effects produces a cosmos where structure is localized and emptiness dominates all larger scales. The meaning of cosmic emptiness emerges from the combined behavior of structure formation, gravitational binding, and universal expansion, all acting together across immense scales of space and time. At every level, from galaxy clusters down to individual stars and planetary systems, matter is organized into concentrated regions separated by vast regions where density remains extremely low. This pattern is not an accidental feature of observation, but a natural outcome of how matter evolves under physical laws. On the largest scales, the universe contains a vast cosmic web of filaments and voids. These structures define where matter is likely to be found and where it is not. Filaments and clusters contain the majority of visible matter, while voids occupy most of the total volume. Even within filaments, matter is not continuous but spread thinly across space. This layered structure ensures that emptiness is present at every scale, above the smallest bound systems. Within galaxies, matter becomes more concentrated, yet emptiness still dominates. Stars are widely separated, and planetary systems occupy only small fractions of galactic volume. The interstellar medium fills space between stars but remains extremely diffuse. Even regions of active star formation represent only temporary and localized increases in density. Once energetic processes disperse material, these regions return to low-density conditions. On smaller scales, planetary systems continue the same pattern. Planets orbit stars through vast regions of near vacuum, and even dense regions such as asteroid belts remain mostly empty space. The structure of matter consistently reflects a hierarchy in which dense objects are embedded within overwhelmingly empty environments. This hierarchy extends seamlessly from planetary scales to intergalactic distances. Energy fields and radiation permeate this empty space without filling it. Light cosmic rays and magnetic fields extend across galaxies and beyond, but they do not add material substance to space. Instead, they move through regions that contain very little matter, highlighting the distinction between energetic activity and physical density. Space can be active while still remaining largely empty in terms of matter content. Dark matter plays a central role in organizing where matter accumulates, but it does not reduce emptiness in a visible sense. It forms gravitational structures that guide galaxy formation and clustering, yet most of its distribution remains diffuse and invisible. Its presence shapes the structure of the universe without filling space in a conventional way. The expansion of the universe reinforces this emptiness by increasing distances between unbound structures. As space stretches, matter becomes more widely separated, and regions that were once closer together become increasingly isolated. Gravity preserves local structures, but on larger scales, expansion dominates, ensuring that empty regions grow in extent over time. The combined effect of these processes is a universe where matter is highly concentrated but sparsely distributed. The total amount of matter is vast, yet it occupies only a small fraction of the available volume. The remainder is composed of regions with extremely low density where particles are rare and interactions are minimal. These regions define the dominant state of cosmic space. The perception of galaxies as densely populated systems is therefore misleading when considered in terms of volume. While galaxies contain billions of stars, those stars occupy only a tiny fraction of the space within them. The same pattern repeats across larger structures where galaxies themselves are separated by enormous distances, and clusters are separated by even greater voids. Cosmic emptiness is not absolute nothingness, but a state of extremely low density shaped by the history of the universe. It arises naturally from the interplay of gravity expansion and initial conditions in the early universe. Matter is not uniformly distributed but organized into structures that leave most space relatively unoccupied. The universe, when viewed as a whole, is therefore not filled in a uniform sense but structured in a way where emptiness dominates most of its volume. Galaxies, stars, and planets represent concentrated exceptions within a vast background of low-density space. This arrangement reflects the fundamental processes that govern cosmic evolution, and explains why a universe containing billions of galaxies can still appear overwhelmingly empty.